Hi, everybody. Good morning and welcome to the class advanced final presentation for today. It is the top of the hour and we're going to kick off. I wanted to welcome everybody to this final presentation from the 6th cohort of the class advanced program, Internet 2's class advanced learning program. My name is Amanda Tan and I'm the program manager for class. For the past 3 years, I've been working on building out our cloud and cyber infrastructure learning programs here at Internet 2. But mostly that just means that I convene really strong participants in our activities, and then I make them do the work. This spring, we have 12 amazing participants in our 6th cohort of the Class Advanced program. And the program really focuses on enabling research and higher education IT professionals to push themselves with learning about the latest cloud tools and technologies and to build something that they can bring back to their own campuses to show the possibilities of the possibilities of using the cloud. So these projects that you will hear about today were made possible by hard work. The cohort built these projects in 3.5 days. There were lots of sleepless nights and amazing brain power, and they were also enabled by credits from Amazon Web Services and Google Cloud Platform. I'm so proud and in awe of everything that this cohort has achieved. If I'm allowed to say so, I think this has been one of the 6 strongest cohorts that I've ever had the privilege to be part of. We have 5 presentations today. 2 focus on building artificial intelligence machine learning pipelines on the cloud, 1 on networking, and 2 projects on Kubernetes and infrastructure as code. With that, I'm going to hand it off over to the first group who worked on AI ML workflows on Amazon Web Services to kick things off. And let me stop sharing.
Good morning, everybody. I am Gustavo Almeida, and I'll be presenting our project as scalable image identification on AWS. Can everybody hear me okay? Good. So this is our team members. We have DJ, have Stefan, and myself. I'm from the University of Arizona, and they both are from UC San Diego. So an introduction to our project is to find what problem we were trying to solve. And our problem was that of the object classification, which is a pretty classic machine learning challenge that is a little different from object detection. So what it does basically is identify what's in an image. So you have an image of an animal, a car, any object. That image is sent to a model. It's trained. The model is trained and then tells you what's in that image. There's multiple applications that can be used, ranging from automatic detection of the surroundings, real-time data detection, computer vision for car, the self-driving. All these kind of applications are used based on this problem in machine learning. And what we did more specifically was a part of the inference of the model. So basically, for machine learning challenges, we have one part, it is the training of the model, and the second part is the inference, meaning that the model has been always already trained, and then we send an instance of our object to be classified, and that's what our model did. So in terms of goals, our goal was to implement an object classification service with a scalable architecture using load balancers to distribute the inbound inference task among different servers. So this task, it can be done in a single machine, but as it grows, we come to a problem that if they're processed linearly, the time grows in the same proportion, and if we have a big workload, we cannot support the classification of the images in the required time. So what we did is to first provide a service. So based on the microservices architecture, a small service and a small test that does a very specific function and solve a specific problem, and return back a response to that. So in more detail, what we had is we deployed a pre-trained model to perform object classification, as I mentioned, implemented as a microservice. We chose to do that because we want to focus not on the whole pipeline of machine learning, and more specifically on the inference part. And that's not, I wouldn't say the more important part, but the part that has more interaction. So usually when you have the training, you do the training with a set of images that you get, and you train the model. And after the model is trained and tested, then it goes to be deployed and do whatever service it needs to do. So for that specific purpose, we use the ResNet 50. Is a convolutional network. Very powerful image classification. It's already a classic. There might be others that might are more advanced, but it's still well performing in the field. It was trained specifically on a project called ImageNet, which is a large visual database that has a lot of categories of objects that are being trained on. So it is able to train and classify objects within those categories, even images that are not part of the training set, of course. We chose to build our project on Flask, which is a Microsoft web framework based on Python to create applications. And that's what's running on the back end. So we have a Flask application running Python and other libraries, and that backend handles all the inquiries and requests to our server. And the inference model we use Keras, which is a library based on Python and backend to TensorFlow to perform the machine learning inferences. In terms of a visual representation of what our solution does is that implements API, and basically we can have a client, can be a browser and an API call that submits an image to our service through a HTTP request as a post request. We have the server listening on a specific URL, like in our case, classified image, and the server do all the processing. And then returns back HTTP response that retrieves what is in the picture and what confidence the model has that is the object that it think it is. So for this case, it has a good classification and it has a confidence of 76%. That's how we read it, that it's indeed a Labrador, picture of a Labrador. So it works in that way for a single request. And our challenge in this case is to move from one single request or a line of requests to allow the service to respond to as many requests as possible. And the one interesting thing is that we go over in the network architecture is that our system is a multi-threaded system, meaning that if it requires multiple threads, it starts new process and the serve is able to serve multiple requests and not having one request after the other as in a line or a single process. So I think now we're going to go to the second slide. They talk about the cloud technologies employed in this process.
Hi, I'm Stefan Kessler. We chose AWS, I think mostly because it's the most popular cloud platform. We started with some basic AWS tools like the Elastic Compute Cloud virtual machines. We went on to create images that could be reproduced in case we needed to scale our system. We also had to deal with a virtual private cloud, which is basically just all the networking in AWS. We put this in multiple availability zones so that we would have some redundancy there. Then we got a little fancier with our auto scaling groups, so we could basically make more AMIs as the workload grew. We'd have more servers available to process the images, and then to balance that load from the client requests, we have an application load balancer, which basically directs the requests to the different EC2 instances of virtual machines. And on the next slide, you'll see basically a visual representation of the basic architecture, which, and this is sort of classic, I think, for AWS, where the traffic from the web page or the API call comes in through the internet gateway to the virtual private cloud. It's the load balancer. Load balancer decides which of the virtual machines that the task should be sent to, and then the client gets the result.
Hi, I'm Dongju Choi from UCSD. So for the project, we follow the following steps during these 5 days of development. Of course, definitely, we initially spent the time finding the image classification model, which is a ResNet 50 inference test. And then the first day design, then consider the whole project with the app for the testing, for the test and implementation. So after that, we did build a server with just one single AWS instance to test the whole configuration and our project goals, and then succeeded. Then after that first test, we start to try the whole system configuration. In part, like network configuration with the VPC for multi-zones and load balancing configuration. And then also auto-scaling configuration. These are all done until the final day. We merge the whole parts together to build one system. After that, we did a stress test with a one single thread and a multi-threaded to see definitely demonstrating the system is taking the stress. Okay, so today, and then we'll show the demo for the public test. Next. Okay, this one shows a single threaded test. It shows here the images sent from client side, which is user sending the images, and then server is replying with the classification of the image types, which here could be cracked ball or particular kind of objects inside the image with the node process node information. This is a single threaded, and then we tested the multi-threaded one, showing the same successful output. These are all going to be shown during the demo and explained better.
So this was definitely not without challenges, as none of us were AWS experts. We felt like we were architecting this from the ground up, even though I showed you a diagram of a very probably common load balancer setup. The error messages that we got during some of the challenges we encountered were very cryptic, and there were several times when we kind of deleted what we had done and started over just for the sake of, it's a sanity check, I guess, because it is really difficult to tell what PC load letter means sometimes. And you know, this is our first time working as a team, and not being AWS experts, it was challenging at times to decide who's going to do what. A lot of times you have to wait for something to be done before you do the next bit, and you know, it would be easy to get a too many cooks in the kitchen kind of situation. So that's, you know, something to think about and definitely plan for. On the next slide, you'll see that we did have big dreams that we didn't necessarily get to in our short week. We would have liked to try to containerize the application, maybe scale it using Kubernetes, and do the infrastructure as code. So, you know, certainly once we figured out the infrastructure that we needed, we could have accomplished that given more time.
Continuing on the presentation, there's a couple ways that we tested our system, and one is the creation of the web interface for testing. First, that is a single image, so we have the opportunity to choose any file, upload to the cloud, and then retrieve a classification. Let me just work with the share here for a second. Okay, good. So I show. So this is our website that's stored in as an S3 bucket. And the idea is that we have a list of images that we can choose from. Those are images from the ImageNet. And from that, we can click on the image, upload, and then they will get a classification right on spot as a response. We can choose any number. It gets right most of the time, not always a classification model. But the interesting part, and I want to highlight, is the process by IP right on the string, the end of the string. That every time that we submit, the image is classified by a different IP. So the requests are sent just to the load balancer, and that automatically get to the other IPs as needed. And then that's a way to show that it works. And they work because they have all the instances running, but also it gets to run more in terms of how much the load we have as well. It will have a policy that shows the scaling based on the number of requests. And for a second part, we have provided a Google Colab for testing purposes. And I hope guys don't break our server. But if that does, that's okay. The idea here, and I'll be sharing in a few seconds, is that we put together a Colab so everybody could run that and try. The version that we have has two parts to it, and I'll go through that. First part, it goes to download a series of pictures from a repository, and then after it downloads those pictures, it keeps sending those pictures to our service. And then in that we can see a couple of things, how it actually classifies the images, and also how it starts different threads, and more than that, how each image is processed by different servers, showing in fact how the load balancer is working. So can anyone share the code with the team? Is that shared through the chat? Okay, thank you.
Tim's got it in there.
Yeah, thank you so much. Appreciate it. So just to walk you guys through the process, if everyone went to the AWS demo, there's a two-part thing I already run, but you might need to run on your end as well. The first block of code, what it does, it's connect to a GitHub repository, downloads 50 images, random 50 images, and create that on the pictures, create a folder pictures. So anyone can run that code. And once you run that, it will start downloading the pictures, the sample pictures from ImageNet, and that will allow the second part of the code to run. It shouldn't take more than 30 seconds. I'm already done through it. Are you guys able to get through the code and run it so far? Okay, so the next part is a way to test our application, and it's the endpoint is our load balancer, and what the code does is just go through all the images in the pictures folder and classify them, so and send it to the system. So when you see here, it is gonna be ongoing here. We have 8 threads, simultaneous threads. They are sending the data to our endpoint. They will have the label, the image label, file name. We have the confidence of the prediction, what the model think it is. And I think the more important part for our purposes here is to see the process by IP. So this is a local host name, is not a public IP, but it shows it shows effectively that the process is being processed, the microservice is being processed through different machines in a way that it doesn't change anything to the user. We can add more machines or remove the workload. We can kick in new instances as well. So and that will keep running for as long as we have the script running. Okay, I think that's pretty much what we had for today. think next steps would be questions, I guess, Amanda, but thank you everyone for being here. Appreciate it.
Yes, so thank you, Stefan, DJ, and Gustavo. Yes, the next step would be questions. So we can spend a couple of minutes on questions. If you have any, please feel free to put them in the chat or in the Q&A. We have a couple of questions. One is, can you speak a little bit more about how do you make the inference scalable? So you have, you have your machine. How do you scale that out if you're looking at multiple puppy pictures?
Yeah. So I think the way that we scale, I'll start with the question, but anyone on my team is more than welcome to help the question. But the way that we work on that is that there's a finite amount of computational power in a single machine to handle the load. And what happens is if we send too many pictures load as in the batch, gets to a point that the machine cannot process that anymore, and the queue keeps growing. What it happens is, as we have a load balancer, we distribute the load over multiple machines as if we had almost linear, double, triple, 4 times the capacity of the original machine. In that way, we can have a smaller cost, I would say, just one machine listening live, a couple. And when we have a higher workload, we can scale that to whatever amount of workload. So if we have a few users, or if it's a batch, someone a puppy aficionado and he loves puppies, they want to know everything about all kind of puppies, he can have a folder with thousands of pictures and send that. And as long as we can kick in, start up new servers, the response time will be keep almost constant instead of growing as they're submitting more pictures to be classified, or we have more users as well.
Great. I think like a tool to identify, to splice images of really cute puppies would be very well received. I just had one more question for you. So Stefan, you articulated challenges because you're all not AWS experts. Do you feel like you are or could potentially be an AWS expert at this point? And if not, what do you feel like the next steps should be to make you an AWS expert?
I'm not going to claim to be an AWS expert right now. I feel much more comfortable than I did, and I think probably learned more than I would, or we all learned more than we give ourselves credit for. I think that we're still, in the fog of war as far as what we've learned. I think that doing a project like this was a great way to just hands-on, like have to make it work kind of thing, and that is always a great way to learn. Going forward, AWS has pretty great training modules and things, and but at the end of the day, just using it is the way that I would go about it.
Great. Thank you so much, Stefan, Gustavo, DJ. Okay, the next team that's going to present is the networking team. I call them the networking team, but there's so much more than that. So I'll let their presentations speak for themselves.
Okay, I'll be sharing my screen for the most part, and then Adam will jump in with sharing his. Okay, there we go. No more technical difficulties. Hi, we're the spring cohort, and we're doing networking IAC project. Team members are myself, Zoya Melton with Duke, Adam Ellington with Duke University, and Jeff Balmar with National Oceanic and Atmosphere Administrator, NOAA, NOAA. Oh, okay. So the objective of this project was to build a quick and repeatable build to host connectivity using the iNet to cloud connection. And we did that by using the internet to Insight Console. So the main plan, we broke it down into 3 steps. We manually created a VPN connection between AWS and GCP. And then we manually created the I2 connection between the AWS and GCP, and then we figure out the Terraform code. We chose these steps because number one, we wanted to make sure the VPN between AWS and GCP worked. We could do that on our own without using internet to networking to connect to the console to create the direct connect on the I2CC end. After we did the VPN connections, we decide to do the I2CC connections. And of course, Terraform, because we wanted to make sure we knew what we were doing before we tried to code it in Terraform. So step one, manually create the VPN connections between AWS and GCP. And Jeff will take over from here.
Hey everyone, so what you have on the screen is kind of the breakdown of the various components between AWS and GCP. So what we observed was to build out this connectivity, it took less components in GCP than it did in AWS to establish the same degree of connectivity. So on the AWS side on the right, we had an AWS cloud. We were in US East 1 for our tests. Inside of the cloud, we built a VPC with its top level subnet associated with it. And then we had a virtual gateway created attached to that VPC. We created multiple subnets, but we had one subnet that had an EC2 instance so that we could generate the traffic between AWS and GCP. A similar architecture on the GCP side in the Google Cloud platform. Once again, in East 1, we had a VPC out of another top level /16 subnet with a subnet created within the VPC and a VM instance running inside of one of the subnets to be able to generate the traffic. Next slide. So what you see here is our phase one, as Oya mentioned, was to build the IPsec VPN tunnels over the internet overlays. What you'll see on this first slide here is that from the AWS cloud side, there were 2 VPN tunnels built to GCP. The first tunnel in the red here, the 18 address is the internet public address that's connecting to the 35.242 address in GCP. That is the outside public connections that was used as the anchor addresses to be able to build the tunnel over the internet. And then there's the tunnel 2, which is the 34.204 address in AWS. That's establishing the IPsec tunnel with the 35.220 address in GCP. Once again, these were the outside public internet addresses to establish the anchor interfaces for the tunnel. And then underneath of that, you will see the BGP information to be able to exchange the routing information. So on the tunnel 1, there were the peer-to-peer interface addresses on a /30 that were established between AWS and GCP. And then there was a tunnel 2 that had another set of interface peering addresses. And this was so that we could establish the BGP relationship to exchange the routes between the 2 environments over the VPN tunnel. That's everything on this slide.
In step 2, we manually created the I2 cloud connections between AWS and GCP. Jeff, you want to go?
Yeah.
Okay.
So what you see here is the Internet 2 Insight console. And on the left-hand side of the screen, you will see the first half of the connection, which is AWS establishing a direct connection to Internet 2. And you will see from where it's established in AWS, where it lands within the Internet 2 routing infrastructure. So you will see here that it's AG3 .Ashburn is the router on the Internet 2 side. The right side of this is the connectivity between Internet 2 and GCP. So what you'll see here, once again, is from GCP, the interconnect connection that it peers with into Internet 2, and it actually lands on the AG4 I2 aggregation router. We'll touch more on that in a moment as to why this is the AG4 router instead of the I2 AG3 router. And that's everything on this slide. So this breaks down the actual connectivity from point A to point B here. On the AWS side, there are two components that actually make up the components to be able to land the direct connect. And that is the direct connect gateway that you see here depicted in purple, and also the virtual gateway, which is the lighter blue image. Now, we could have had the direct connect land directly on the virtual gateway. The reason why we didn't do that is because the virtual gateway is region specific, where the direct connect gateway is region agnostic. As I mentioned earlier, we're built out in US East 1. If we did want to expand to another AWS region, having the direct connect land on the direct connect gateway allows us to attach to other regions without having to provision new direct connects. On the GCP side of the connection, the interconnect that's provided from I2 lands on a cloud router. And what we did from here, similar to what we did with the IPsec tunnels, is we have peer-to-peer interface addressing, but this time instead of peering with each other on both ends of the VPN tunnel, our peering actually establishes with this purple router in the middle here, which is the virtual routers on the Internet 2 side. So there is one peer-to-peer interfacing assignment between the Direct Connect gateway in AWS with AG3 Ashburn on Internet 2. And then there's a different peer-to-peer interface addressing network, which is between the GCP cloud router and the AG4 Ashburn AG router within I2. And what you will see here, this is how the routing and an exchange of routes happen. The 10.0.0.0.16 prefix is being learned into GCP. And if you'll notice, that is actually the /16 that exists locally within AWS. And then on the AWS side, it is learning the 10.1/16 prefix, which is local to the GCP platform. And that's everything here. So on this slide, you'll see the BGP peering statistics in AWS. The first information you see here is the BGP session for the Direct Connect. You'll see the peer-to-peer interface information that we captured on the previous slide, and that's how we're peering directly with I2. And then below that, you will see the VPN tunnel BGP peering statistics. You'll notice that there's actually two tunnels. This is for diversity. So if one of those tunnels goes down, it would roll over to the secondary tunnel. And in this scenario, we are using those public internet external addresses for the VPN anchors. And we have the inside interfaces, which is what is provisioned on the actual interfaces to maintain the BGP connections. That's all here. On this side, this is the BGP peering statistics in GCP. The top section here shows the ASN that we used for the VPN tunnels. And here you'll see the two green check marks. That's because we had two BGP instances, because we had two VPN tunnels running. And then below that, you'll see the ASN we used to bring up the GCP interconnect with only a single BGP instance. What's interesting here in the lower section is within GCP, there is one delta from what we observed in AWS. In GCP, you can actually set basic BGP route preference configurations. What we have here is setting 0 on the interconnect path, to where 0, the lower the number, the higher the preference. So 0 is the highest preference, saying that any of the prefixes advertised out of BGP, that should be the preferred path. So when AWS receives this prefix advertisement from BGP, it will prefer that path. On the right-hand side, you will see an advertisement value of 100, which means that it's a less preferred advertisement. So when it advertises this prefix out of BGP, when AWS receives this prefix advertisement, it will treat this as a lower preferred path. It is ideal though, because in the event that the broker connection were to go down, there would be another path in that table, though less preferred. It could begin routing that traffic over the IPsec VPN tunnel. The one delta here from AWS is that AWS does not actually allow you to influence any of the BGP route preference settings. You have to set that on the remote end, and that's why we set that within GCP. That's everything here. I can hit this one as well. So what we're demonstrating here is that when we have this connectivity up, we are able to communicate across this link. So you'll see the 10.102, that is the local private address assigned to our VM instance in GCP. And we attempt to ping 10.0.0.47, which is the local private IP address assigned to the EC2 instance in AWS. And we were able to establish that connectivity. Obviously, when we're talking about from one cloud platform to another cloud platform, there would be no way for this to happen, communicating with private addresses if we didn't have this dedicated communication established between the two platforms. That's all here.
This slide shows the opposite, how we're communicating from AWS to GCP. So it works both in both directions. Jeff?
So what you'll see here is to verify that we actually got something working and then intentionally broke it. The first thing that we did before we built the IPsec VPN tunnels or the cloud broker connections through I2 is we leveraged the public assigned addresses on both the VM instance and the EC2 instance so that we could say there is connectivity here. So what you'll see is, to begin with, this is the public address, the 44201 address. This is the public address assigned to our VM instance in GCP. From the outside world, we were able to communicate with this public address. And then Zoe, if you want to apply the, oh, excuse me, this is our EC2 instance in AWS. If you want to apply the security policy, you'll see after we applied our AWS security policy, pinging from the same outside external host to the 44201 address, we were no longer able to reach that public address assigned to the EC2 instance. Same thing here, checking the logos to make sure I'm talking about the right CSP. And so in this one, it's the public outside. We tested again to make sure that we could hit the public external address assigned to our VM instance in GCP. In this scenario, it's the 35.211 address. From the outside world, we were able to ping the 35.211 public address of the VM instance. And then Zoe, if you want to apply the GCP firewall policies, you'll see that from the same external host trying to ping that same 35.211 address, we were no longer able to establish communication. So, and once we got to this point, the only way that the two environments could communicate is over the connections we provisioned for IPsec and the broker connections. That's all.
Sent over to me. So this part, really the goal for this task was to translate the steps performed in the provider consoles into the IAC configurations, right? So, several of the main reasons for this is, I guess, one, efficiency. So, if this is something you're doing repeatedly, you most likely want to automate it, right? And by doing that, you're going to have more consistency. So, that's going to avoid things like, configuration drift, which, could lead to misconfigurations or worse, possible security incident from one of those misconfigurations. So, when we started this process, we had kind of two goals in mind. We had, we wanted to establish connectivity with the VPNs, and then we wanted to do it through third party, like, the internet too, with the direct connect. But, when I started this, it seemed like there was an issue where, and when you're trying to configure this, there was settings that were needed, but you didn't have until you actually configured, part of the, like the gateways on either side. So like you would need to have the public IP available, but you couldn't have that until you created the gateways. So that's when I kind of shifted over to looking at the direct connect option. And so share screen with this. And we basically, so over on the GitHub page, we basically start kind of here in Terraform. So the idea was to find the modules that you needed or the resources in Terraform that kind of match up with the steps that we took in the console, right? So that we could so I would know exactly kind of the process that's needed to do this. So in the beginning, we basically build the GCP, the VPC, and then from there, well, we're connecting to the provider here, and then here was where we create the VPC, and then from that we create a subnet, in that space, right? And then back over to AWS, we're going to connect to that provider as well. So and for this to work, basically, I've already went through and created like the service accounts and gave them, the most narrowly defined credentials that I could, so they have the permissions to, connect to these spaces and be able to create these resources. And for this example, basically, I just stored them as environmental variables in VS Code. So when I run this, it automatically knew about the credentials and would be able to connect. Like in a production scenario, we'd probably store in something like a vault. Like it seems like HashiCorp has a vault, so they can be securely decrypted and retrieved and things like that. So, once we make that connection here, we're basically going to create the VPC again, very similar to the steps in Google. So then after that, we're going to create a subnet space here with 10.3.1.0/24. And then after that, we're going to create virtual private gateway, which is needed as part of the direct connect to get established. This is like your door out of your VPC, getting out the front door, basically. And then so next, we're going to attach this virtual private gateway so that it's, functionable. And then there's also a prefix we have here we have to associate with it so that our 10.3.1 address is advertised, I believe was the terminology. And then a part of that as well, we have something called an internet gateway, which basically means, which is needed for the purpose of traffic being able to go outbound to the internet from your VPC. So maybe, for like say the purposes like want to browse the internet, or if you have maybe machines in the cloud and say Microsoft and you want to update them, and point them to Microsoft to get updates, you could do that. So it could, get out publicly to the internet. And from there, basically, so that can work, you have to create a route table. And so this is basically so the traffic kind of knows where to go, right? And then for there, we have a manual entry added for the internet gateway with a destination address of 0.0.0/0, basically indicating to the outside the public internet. And then once that's done, we have to associate that route table with the subnet we created originally, and that's essentially what's happening here with this. And so from there, basically, within the AWS, in terms of firewall policies, they use something called security groups, which can be confusing. It was pointed out in our, one of our sessions last week. But essentially, what this does is this is how you can create firewall rules, right? And so in this example, this case, we had, port 22 incoming or ingress from basically this particular block here, or that's from GCP. As well as ICMP. And ICMP doesn't really use ports in traditional sense as other protocols. So security groups in Amazon allow for something called types or codes. In this case, 8 and 0 for echo requests. So it can accept those in addition to ports, so that those pings and ICMPs are successful. Once you make that exception there. So ingress from GCP network that we made. And of course, there's egress here to allow outbound traffic. I don't know if we need to do that. I think that's there by default. But then when we flip over here to Google, we do the same thing again. So we allow port 22, we allow ICMP, and from the 10.3 address that we did, that we had created and Amazon. So we did a lot of this, but unfortunately, there's still a dependency on the work that needs to be done from Internet 2, with that virtual interconnect router, in the sense, in their data center to make those links happen. So basically flip over to the command line, and then, if we want to run that, you can kind of see that in action, right? So hopefully everything goes as planned here. So you're going to see it says, hey, we got 13 items to add here. And we're going to say, yeah, let's do it. All right. So, and it's basically going to run through and kind of go through that, that sequential order, and kind of walk through those steps as we've outlined, over in GitHub, which I have here in front of me. So, once that's done, we can basically pop in the two consoles and refresh them. And, we should see these new additions here for the new VPC, the subnets, the routing table entries, the firewall rules, things like that. So hopefully that should be done here momentarily. So once it is, we'll flip over. Pretty close. Let's see, while that's running, we can go ahead and all right, so that's complete. So it added 13 additions there. So now if we go over to over here to the consoles, zoom out of the way. So if we refresh this page now, we should see under VPCs, we should see a new one. So we do. So if we go into here and we'll click, you can see that we now have this Terraform VPC. And then under subnets, we have a Terraform subnet, which we saw. And then route table, we'll have a route table there for, that's this one here. It's going to be the top one. I don't know if I can see the name for it, but it should be that one. And then if we go over to the security section, we got, we'll have the security group here where we sign that. So SSH and ICMP here. And then if we flip over to the GCP side, and we'll refresh that, and we should see a VPC show up here. So for Terraform. And then if we go over to firewall, you can see here that we should have one to allow SSH and ICMP from AWS. Then you can see that here from these two. So, when we were working through this earlier in the week, there's a lot of steps involved in trying to do that. So, so with this particular way now, that we can kind of have that consistent and done, for us in a much more efficient way. So that is basically deploying most of that infrastructure as code, here as part of that demo. So I'll pass it back over to Zoya now.
Okay. Oh, let me start sharing my screen again. Okay. And so we took a look at the differences between VPN and Direct Connect. With the VPN, it's a virtual private connection over the internet. It's quicker to spin up, so it was just easy peasy. It's more cost effective, and it relies on encryption and security measures. And it traversed through the internet path. So we really have no say-so in the paths that it takes through the internet. However, with Direct Connect, it's a physical dedicated connection. It's more complex to set up because we also have to work with the third-party provider for the connection. It's very low latency because it is a dedicated connection. The connection is more secure, and the traffic routing is already deterministic because it's using a dedicated connection. If we take a look at the direct connection, using a dedicated connection, we see that when we ping from one cloud service provider to the other one, we see that it's only 16.3 milliseconds. However, when we use the VPN connection, we see that it's a higher latency with 58.969 milliseconds. Milliseconds isn't that long. However, when you're using an application, that latency can make a determination in how fast your application processes data. And then we also took a look at the cost. And I'll let Jeff go over the chart.
All right, so when we're deploying resources into the cloud, cost is one of the main factors, right? So what you'll see here on the cost slide is we broke down on the AWS section the two different connections that we provisioned, the direct connect and the VPN tunnel, and we did the same thing for GCP for the interconnect and the VPN tunnel. What you'll actually see is we broke two different use cases down. If you transferred 1 terabyte of data a month, or if you transferred 10 terabytes of data a month. So in the first column, you'll see for egress costs, that's how much you're paying for all the data exiting your environment, riding across these connections, that the egress cost went up substantially when we went to the 10 terabytes a month for the VPN tunnel. If we look at the runtime costs, these were consistent because this is just what is your hourly rate to have this particular component provisioned within your environment. So these were kind of static fixed costs. So what it breaks down to on the AWS side is if you're transferring 1 terabyte of data a month, the VPN tunnel is substantially cheaper than having a direct connect provision. But as you have more data egress your cloud environment, the direct connect becomes significantly more cost effective, right? So where we go from 1 terabyte of data egress a month to 10 terabytes of data egress a month, you could see the change there as far as what the cost effectiveness is. Same scenario we saw with GCP, actually, but on a further scale. Their VPN egress costs are actually 11 cents a gigabyte, which where it's 9 cents a gigabyte in AWS compared to the direct connects on both for the direct connect and interconnect, which is 2 cents a gigabyte. So what that equated to over the 1 terabyte a month is the VPN tunnel was definitely more cost effective. But once again, as you send more data out of your cloud environment, the broker connection becomes substantially more cost effective. The one caveat I will call out here is that the VPN tunnels do have redundancy. That's why it's $72 a month fixed cost instead of $36, because you're actually paying for two different VPN tunnels. But the direct connect and interconnect, it's only a single connection without diversity. If you did want to provision diversity, you would have to increase your runtime cost because you would have two connections running simultaneously instead of just one. Egress costs would still stay about what they are. Everything here.
Okay, there, I'm unmuted now. Okay, so we bumped into a couple of project issues. It was a learning curve with trying to figure out the AWS and the GCP and also the Terraform. Jeff could speak more about the provisioning issue on I2.
Yeah, we did run into a provisioning issue within the I2 Insight console. Unfortunately, our lab mentor, Scott Taylor, was able to ping the backend I2 engineers and help us out here. So if you remember in the diagram earlier that we showed, we were ag3.ashburn on the AWS connection, but we were ag4.ashburn on the GCP connection. When we set this up on the ag3.ashburn router for the GCP connection, it would not come up. It's set in this pending state, and there isn't really much else we can do other than sit there and watch it and refresh. And it just stayed in this pending state. Scott was able to ping the backend engineers, and they mounted us and migrated our connection from ag3 Ashburn to ag4 Ashburn. And as soon as they migrated us over to the other I2 ag router, the connection immediately went to a fully provisioned state. So that was one of the main challenges we ran into. That's everything here.
And Adam, and I know with Terraform, we had some issues with that as well, some little problems.
Yeah, sure. I mean, I kind of touched on it a little bit before, but just trying to deal with, and creating the dealing with the VPN connections, requiring the external IPs to be available, but you can't have those until you create the VPN gateway. So that was kind of a challenge with that. And of course, even going the direct connection route after you create everything, you still have to have that, connection, in place from the third party, in this case, Internet 2, through that Internet Connect, routing router, so that so data can flow from, one side to the other. So that was it.
So the future of the project is to finish completing everything that we were supposed to do as far as automating the connections using Terraform. Are there any questions or comments or anything?
Great, thanks, Zoe, Jeff, Adam. Thank you so much. Actually, there's just one question. Could you articulate or maybe explain a little bit what a use case, like a real life use case, might be for the project that you had?
Yeah, certainly. So I'll hit it first, and others can add in. So the scenario we're really looking at here is, even if you're not in a multi-cloud environment, if you're in a hybrid architecture to where you have a cloud architecture, but you have an on-prem data center that does data processing, dissemination, whatever else, there has to be a way to distribute that communication and that traffic reliably and securely. And this is a way, especially with the broker connections, to where you can have private network peering just like you would in a single facility or a single campus, but from an on-prem environment to a cloud environment through this hybrid connectivity.
And then maybe one question for Zoe and Adam. So Adam, you were coming into this project pretty green on Terraform. Do you consider yourself a Terraform expert now? And maybe perhaps, just very quickly in 30 seconds, Zoe and or Adam, what would you like to learn more about to help you move things like this forward?
Well, go ahead, Adam.
Yeah, so I would definitely say I was green with the Terraform. I had some understanding of it because some of the work I did kind of over the last year with Ansible and our virtual computing space. And, so I kind of started, making me aware of other things like Terraform. So I did do some research with that, ahead of time. And so being able to apply that here definitely gave me a lot of good experience and eye-opening to, a lot more use cases, how it'd be useful. Obviously, as I noted before, if this is something you're doing all the time and creating, spaces like this in the cloud, you're able to automate it and just make it more efficient and faster, and ensuring that it's configured the same every time if that's what you're looking for, to kind of avoid misconfigurations that could lead to other problems, down the line. So definitely all good things there.
Yeah, and I was very much green, still green, and that it was a very good learning experience with it. I follow Adam along more than anything, but really just applying it and using it is very good. And the GCP, the difference between the different cloud providers and how they configure things, it was really interesting with this project as well.
Great. Thank you so much for that feedback, Zoe, Jeff, and Adam. We're going to move on to the next project, which is about Terraform again and Kubernetes. Mike, the mic is yours.
All right, great. Thank you, Amanda. Just by way of introduction, my name is Michael Peterson. I am a senior IT analyst at Duke University, and I am concentrated in the, my focus is on supporting research computing in the College of Arts and Sciences, mainly in the natural sciences. So that is definitely a growing area of compute usage and cloud usage as well, along with just about everything else, it seems. Excuse me. So the project that I had was, as Amanda alluded to, trying to set up research computing specific infrastructure as code. And so this is a little different than the things that my colleague Adam has done with this. they were very specialized. You'll see his Terraform files are much more involved than mine. Mine is a little bit more boilerplate. I too was very new to not only cloud computing, but especially any of the tools. I knew some of the words. Should I put it that way? I knew some of the words, but I hadn't used any of the tooling or anything yet for the cloud. So that was the first thing that I had to do, was kind of familiarize myself with some of the tools. And I focused my project in Azure because I wanted to use Azure because my institution uses Azure mostly. I won't say exclusively, but mostly. And so I figure if that's the environment in which I have the most support locally, then that's probably the best route for me to go. And so I will go ahead and yeah. So my project originally started with the goal of setting up a Kubernetes cluster with just getting my screen shared here. So a Kubernetes cluster running Jupyter Notebook, Jupyter Hub in particular, and that I didn't quite make it there. Well, I did, but I really got interested in Terraform and how that works. So these are some of the instructions that I've made and augmented. Some of the things that were needed. You need the cloud provider command line interface, and all three of the major cloud providers have one that work on Windows, Mac OS, Linux. And of course you need Terraform, which is by HashiCorp, and those are the two main things. These later ones I may touch on just a little bit, but for controlling the actual Kubernetes cluster that I created. But really it's pretty simple. Well, I say simple. I started out with Terraform files that would just go out and create a VM. And I learned a lot through that because the stuff that I found didn't quite work. It almost worked, but not quite. And so I learned a lot in kind of debugging that. And then once I got that working, I was like, wow, if it takes this much, which isn't a whole lot of Terraform code to create a VM, you know, like you saw in Adam's example, there's a lot of steps, all right? To make a Kubernetes cluster in the cloud, you need a VM, at least one VM, preferably scaling VMs, you know, and all the subnetworking and all the, you know, you just need all the pieces, right? The networking, everything. You just got to create it. And Terraform has the ability to run modules where a lot of the cloud providers and sometimes in coordination with HashiCorp create these modules for you to use. So I found one called AKS. Basically, it's sets up a Kubernetes infrastructure in Azure. And so once I had that, there was I had to set, I think, just a couple things. In fact, I can show you. I can click. There we go. So this is kind of the very beginning part of a Terraform configuration where you specify the resources, not the resources, but the providers that it's going to use. Basically, the things that you're going to download HashiCorp, you know that Terraform is going to need to know how to do. And you can see all these things are versioned. And that's something I think that is very important too. They specify a minimum version. And this space is changing so quickly, and has been since it started. It's just changing so quickly that it also has the ability to set maximum versions, which would probably be a good idea to block things from trying to use if I say here the Azure RM, the Azure Resource Manager, it has to be at least 2.0. I should probably also include the caveat that it really should be less than 3.0, because the major versions can introduce breaking changes. And so that's something I should probably set so that it either warns me or it will grab the, a 2.x version of the Azure RM provider when I run it. So Terraform keeps track of all these versions and doesn't throw anything away, and it will use what you have specified, which goes a long way in making sure that the code still works, even 6 months from now, because that is a definite problem in such a fast moving space such as this. Moving on to the main file here, where we define some resources, as you saw with Adam's setup. These are all pretty, I'll get to the top here, pretty straightforward. One of the things that I liked about Terraform is their resource random pet, which gives you, basically it returns an adjective and a pet, an adjective and an animal. So I think I've had things like chilling chiggers and so I've, resources named after, voluminous rhino and, crazy things like that. It just kind of, make you smile a little bit as you're working through here. And so it, let's see. Oh, this is even the wrong one. This one. Sorry, that was the wrong one. This one, yeah, because this is the module that I found. So in my work setting up the VM with Terraform, that's where in debugging that one, I really started to develop, I should say, kind of an intuition for how this works, and noticed in my searching that, there are these modules, and this AKS modules especially is just saves a ton of work. This is, the main part of my Terraform infrastructure. AKS sets up the Kubernetes structure, the Kubernetes cluster for me. And I just have to specify a couple of other things, the resource group to run in. Let's see, that was that one. And then there's another file here that just sets some variables that needed to be set. And then it goes out and runs the code and creates the Kubernetes cluster, which I could then go back and install the Jupyter Hub container on, and was able to see, this has some instructions here for both for all the cloud platforms to some degree, and then the Kubernetes was new to me too. I'd heard it, but never used it, much less configured it, and so I had to do some searching to basically learn a lot about it. Just like with Terraform, these last 2 weeks have been a lot of learning for me. Cloud is, I don't think the word cloud is even in my job description. So this stuff was all new. At least it's not now. It might be after this class. We'll see. So then once the structure once the cluster is set up, then you can configure your Kubernetes client so that you can then use something like Helm to deploy the Jupyter Hub and then, you know, further further customization that you might need to do. And so in terms of challenges, it almost all was a challenge. I am very familiar with command line interfaces, so that part was not, I'm not afraid of the keyboard at all. I prefer it. In fact, keyboard shortcuts are a great thing. But just getting my head around Terraform, how it works, and it helped a lot once I had developed a little bit of that intuition for how Terraform works, and so it helped me search for things, look through documentation, and kind of helps me get, you know, figure out what's important and what's not a little bit more quickly. And you know, as I said, this is a very fast-moving space, so a lot of the examples that I found didn't quite work anymore, and so, you know, have to tweak them. And so it's a good idea to, that's why I mentioned the whole versioning thing. That was something that I think is very important. And so so this document is one of the things that I was working on. I still need to flesh it out a little bit with some of the other stuff that I've done, but it's at least a start, and I hope it will be helpful for others who may just be starting out as well, and kind of give you a hand up to learn how to convert your infrastructure into code, cloud infrastructure into code. It's I think it's a great thing. You know, all the advantages that Adam mentioned, the reproducibility, that, you know, as someone who doesn't do cloud, you know, if I can do cloud, it's probably not something that I'll do every day. And so being able to have this reproducibility, you know, in infrastructure as code, I don't have to remember to click here and then click there. It's just, it's in the code. And, you know, if I need to do similar things in the future, then it's all right there. I just have to figure out the code, remind myself what all that's about. But it'll mostly work. So I'm hoping that this will allow me to have better informed conversations with our central IT folks about cloud computing, specifically in support of researchers. And even it was really nice to kind of get my hands on the different cloud platforms these last 2 weeks, so that when I do talk to researchers, you know, who want to scale out their computing, you know, I have a better idea of the language. I have perhaps even some ideas on how we might go about it. So, and I hope to be able to bring that back to the researchers that I support. And in terms of the long-term goals for this project, like I said, I hope it's useful for others to learn Terraform and give them a leg up on their cloud journey. And with that, I will send it back to Amanda.
Great. Thanks so much, Mike. This was really great. I'm so happy to see you being able to use Terraform and Kubernetes. Those are not easy tools to learn in 3 short days. I guess maybe just one quick question for you now that you've had your hands in both Azure and Google Cloud. Do you have a favorite?
I don't know that I do yet. I don't know that I do. And honestly, now that I know about Terraform modules, I think I may have a preference for Terraform module authors rather than platforms themselves. Because like I said, I found that Azure AKS module for Azure Kubernetes service, and that was, you saw, very easy to work with. I found a similar one for GCP, Google Cloud Platform, and it looks similarly pretty simple. There are a few more required variables and things you have to set. But yeah, it kind of, that's the thing about the code, right? It kind of abstracts all the differences away. And so, I mean, still the language differences that they use, you do need to have your translator hat on when you are moving between clouds. And hats off to the networking team who had to do that like all the time this week. But yeah, it's I can't say that I really have a huge preference, but I could definitely see myself in the future having Terraform module author preferences.
Great, thanks, Mike. So Terraform is your favorite. None of the cloud providers, but Terraform. Okay, great. Thank you so much. We have 2 presentations left, so we're going to move on rather quickly to Fernando. You're up next.
Hello. Can you hear me?
Yes, we can.
Okay, so give me just 1 second. Closing some tabs over here. Gonna go as fast as I can. Just give me 1 second, please. So you want to see this? Okay. So I'm guessing you're watching my presentation, right?
Yes.
Okay. So I'll try to go on a different page here. So the title of my project is Automation of a Kubernetes Cluster with Terraform. So I had an app that was already created, and the idea, the idea was to automate the process of bringing that app up using Terraform and Kubernetes. So a little bit of me. So my name is Fernando Garzón. My role is I work at UCSD. I'm a research scientist, specifically at the San Diego Supercomputing Center, which is at UCSD. Have 2 main roles: one in the user support side, and one on the software development side. I'm currently working on a blockchain network, and the idea is to be able to port that blockchain network using Kubernetes and probably also Terraform in a public cloud environment, to enhance all the deployment process and focus specifically or improvement of the CI/CD pipelines that we currently have. So that's why I chose this project. So very fast project overview. So the name, Automation of a Kubernetes Cluster Deployment with Terraform. The main purpose is to streamline Kubernetes cluster deployment using Terraform. That's all I did in this project. So the goals of this project. So you can see them here. Build a pipeline that automates the deployments of the Kubernetes cluster in a cloud provider. This pipeline needs to provide networking, persistence layer, and secrets management, and demonstrate the benefits of investing time and resources in automating just once versus deploying manually. So I did that. I deployed this first manually, and then I deployed this automatically using Terraform, and I'm going to show you a little bit of that later. The use case for this was a very simple app, simple yet innovative app. So this app essentially facilitates the creations of offers and posts, connecting people. So it connects individuals who need to ship items with travelers who have some spare luggage space. So this platform works as a broker essentially, and it will allow travelers to post available space in their luggage and their destination, while senders can create offers on those posts, emulating some sort of a bid. They offer how much money they want to pay for getting their stuff shipped with the traveler, and the traveler can choose the best offer among several senders, let's say. So you can think of it as an Uber delivery service, only with air traffic instead of cars, more or less. So this app was already developed before I started the project. So I had a series of microservices that were working and communicating properly. They were also unit tested. And there were some end-to-end tests locally developed with Docker Compose, as well as some automation with the test with Postman. So that was done before this. So the first thing I wanted to do is to actually make sure that those tests actually worked. This is the architecture. I'm not going to go deep right now into this. The first step was to test that the app worked locally, and then to migrate that into a Kubernetes cluster in the cloud. So the first step in doing that was to create an artifact registry in order to enable the cloud providers to access the images of the microservices and then spin up containers. The second step, maybe you want to see this slide instead. The second step was to manually spin up Kubernetes network with a persistence layer. So that was done in order to enable the containers to read and write the transactions they perform in the database, and ensuring that we're not losing any data in case the microservices break. So you know that if a container goes down, you'll still have persistence of the transactions. The steps involved in the networking of the whole system to enable the communications between the Kubernetes cluster and the persistence layer was done manually. Took a little bit of time, of course, and a little bit of headache as well, but it succeeded. And finally, once all that was up and running, the final step was to do the deployments with the kubectl tool. And that all worked nicely, but that was all done manually. So the whole idea of the project is to be able to port that into a more automated pipeline, or more less hands-on and more hands-off the whole process. So what I did was to just migrate all these steps to a Terraform script, and I'm going to show you the results in a little while. But the steps here were like very simple. Just migrate all the steps manually into a Terraform script and just run the Terraform and watch and relax. That was essentially what happened, because it was really easy to do that. And I'm going to show you the outcomes in a little while. So the outcome of this project was the deployment of a functional cluster connected with a persistence layer. So that happened automatically and manually. And the orchestrating of the communication of several microservices to achieve the business goals that I mentioned earlier. So I'm going to show you what how that really looked like in my actual deployment. So I'm going to close all these. You don't need to watch that. So, okay. So here I'm going to start with the repo. I'm going to try to go real quick over here. So here you can see all the microservices developed here. There are Docker files inside each of these folders that will enable the creation of the images in the artifact registry in Google. So I'm using Google for this. And essentially, here are the steps. So first of all, I created the artifacts. I did this manually. I'm sure this can be automated via Terraform, but I just did it simpler than that, because I wanted to check only the deployment of the Kubernetes cluster with its networking and the database. So this was done manually, although you can easily, I think you can easily create these artifacts using Terraform. I want to show you the Terraform cluster I created. I don't want to show you this one. I think I want to show you this one instead. Yeah, so I want to show you this one. So this is the cluster I brought up using Terraform. I hope you believe me that I did this using Terraform and not manually. But the cluster is up, essentially. You can check out the code here to check that the name actually matches. If you take a look at the Terraform script, you can see that when bringing up the cluster, but the cluster has this name. This is the name over here. So I hope that is proof enough that I brought this up using Terraform. The cluster is working, it's up and running. I also was able to bring up the persistence layer and also to connect this persistence layer with the cluster, which is not as straightforward as you may think. If you do it manually, that might have a little bit of headache. But I was able to automate that using Terraform. So you can see here that all the networked stuff and the database that I was able to bring up, DBS and Terraform. So that's over here. And I want to go a little bit into the architecture. So we need to take a look at this real quick. So the Kubernetes architecture, it can be a little complicated, but essentially what it does is to connect a bunch of microservices and automate or make the API calls like do something logical and something that aligns with the business logic. One of the main components of this architecture is the ingress. I'm sorry it looks so bad here, but in this image, I'm trying to show that this deployment has a unique point of access, which is this ingress, which works like a gateway API. And this ingress will route all the calls to the right microservice. There is also a little bit of orchestration amongst these services, these microservices. So this RF003 microservice will connect with another 2 or 3 microservices in order to make transactions that involve several microservices, kind of a very split responsibilities by each microservices, which is one of the best practice you can do in this kind of deployments. So the ingress is there, and the ingress is here actually running. The ingress part is very important because it's where you access the whole application. And when you bring this up, you'll be provided an IP address over here, which is easily accessible. And the only thing that you need to do once this is up and once all the other microservices are up is just to copy paste this API address and to try to test it out using a tool like Postman or if you want to do it through command line or whatever. So I'm going to show you what this looks like. So remember, this is the IP address. And these are some tests I ran just this morning before we started our meeting. And this is a collection I have. You'll get access to this collection if you check the GitHub repo. But essentially, this collection will connect to the ingress API, which is here. You can check that this address over here is the same as the one that is over here. Exactly the same. And when you run this, you'll have a set of tests. And this will just go over each test and check if it passes or not. So I ran this morning. They were running just fine. It is probably running as well if I run the test again. And that was the outcome. That was the bit outcome. So I was able to bring this up using Terraform. And the long-term goals. So there is plenty of automation that can be still done on here on this deployment. Artifact registry, for example, the artifacts there can be automated in order to be the loaded into the artifact registry. The The backend can be improved in haste, can be more complex in time. You can add more stuff there if you need, but it at least the pipeline at least provides a very solid product in order to add to that. And that's basically what it. Thank you very much. I hope you enjoyed this presentation.
Great, thanks, Fernando. That was great timing. I did have one question for you. So it looks like you were trying to get some sort of transportation app. Can you maybe talk a little bit more about how you would plug in other kinds of use cases into the setup that you developed?
Yeah, so for example, maybe this is too boring to show. Okay, so for example, now I think I'm gonna need this. So there is one thing, there is the security regarding what you're transporting, right? For example, if you are offering your services of transporting something for somebody, you wanna make sure that the items that person is shipping is something legal, right? You don't want any, you don't wanna have problems with it. So maybe you can add a process in the app or a series of microservices in the app that makes sure that the items you're transporting are legal, are safe, that are not going to get you in trouble. So that can be added into this setup, let's say, into this app, sort of new functionalities. And you can add as many functionalities as you want, as long as you are like very rigorous with what the requirements are. And since they are deployed as microservices, and they will be obviously containerized, and you will be able to create those microservices, to deploy those microservices using Kubernetes. And if you can test them locally and also in Kubernetes. And if they present any issue, you can just roll back those microservices very easily. So those are like the use cases you can think of. Like you can be very creative in adding as many requirements or microservices you need to make your business logic run as you want.
Great, thank you so much for this. Thank you. And we're going to move on to our last presentation for the day. This will be the AI ML workflow on Azure. Go ahead, Drew and team.
Hello, everybody. We focused on providing an Azure AI ML pipeline for this course. Introductions, the team of four, we are all from Duke University, but different groups. We have Barry Snyder, who is a senior analyst in monitoring, Jim Wood, a full stack engineer, Steve Rich, senior engineer, identity and access management, and Drew Stennett, senior analyst, system security lead. What we're going to do through this presentation, I'm going to lead through the slides. Then Steve and Barry are going to talk a bit about our Terraform deployment when we get there. And then Jim is going to do a demo of how the pipeline actually works. We only have roughly 200 slides, but I'm sure that we'll get them done really quick. Don't worry. That's a joke, not really 200 slides. So we all came from varying levels of cloud experience. But I think we all had a pretty good time doing the 1 week training and then working directly together over this past week for the group work. And we were all sort of interested in this AI ML pipelining piece, which is how we all got sort of put on this project together. Our objectives, we really had one big objective, and that's to create a platform for data scientists or researchers to run AI and ML pipelines. We really wanted to use GitHub for researcher code, and we wanted to be sure that it's scaled. And we also wanted to be sure that it's not like super expensive, because not all of our researchers have tons and tons of funding. Why do we want to do this? What I think the big reason is we want the researchers and data scientists to be able to focus on what they do best, which a lot of times isn't creating these sort of cloud pipelines. So we want to build a platform for researchers to run their pipelines and make it make it easy for them or seamless so that they don't have to sort of think about these back-end platform things. They can just do the stuff that they're best at and not worry. We also wanted to allow for some different funding models. Some of our researchers have lots of funding. Some of our researchers have minimal funding. And we wanted to make sure that we had something that worked for both of those use cases. And then our final goal, and this is a little bit big brothery from Central IT, is we also want to like have a view into things. A lot of times when we don't provide things to research, if we don't provide the right things to researchers, researchers will go out and just sort of do it on their own, which is totally great for the researchers, but we also want to be able to have some accounting in place for monitoring security policies, and as well as costs and things like that. What we actually got achieved, I feel very proud of what all four of us got done. We were able to fully automate the infrastructure with Terraform. We have a working example of a pipeline that a researcher could clone and tweak to whatever they want. We also ended up with a machine learning workspaces that researchers can interactively test their Jupyter notebooks on. And then we have a little option of using pre-built clusters for machine learning or generating a completely custom cluster if the researcher decides to do that from within their project. Technologies used, Terraform. Hope everybody's not sick of hearing the word Terraform all morning, but it's great. I think we all love Terraform. Worked awesome as doing infrastructure as code. We wanted to use GitHub as a shared code base, just as it's the most popular platform for sharing code out there. So a lot of our researchers live in GitHub. And then we used a ton of Azure. Azure was the only, I won't say the only cloud we used in this project because we did touch into GCP a little bit, but Azure is what we, Duke, as a university, mostly use. So we wanted to try and stick with that since that's sort of where our leadership points us. The pieces of Azure that we use were the machine learning workspace and studio, and we'll talk a little bit more about that shortly. We're using Azure storage accounts for actual data retention. Those are sort of Azure's way of providing S3, although it's not actually S3, it's a different thing. We're using Key Vault for secret storage, application insights, which means metrics. I don't know why it's called application insights, but it's great to have metrics. And then we're using some log analytics in there as well. This is the four of us drinking the Azure Kool-Aid. So delicious. Tasted really nice, very refreshing. And we already sort of talked about this bit, but the Azure piece really did work well as far as integrating with all of the pieces we needed. And I didn't feel like we really had to chase down too many rabbit holes since we were all staying mostly self-contained in Azure. The architecture we used, it looks a little complex here, but once you sort of wrap your head around it, it's not too bad. We used Terraform to build out all of the pieces. I think sort of the three main pieces were the Azure Learning Workspace, the storage account, and then just sort of these miscellaneous utilities like the Key Vault, log analytics, and application insights, none of which the researchers are going to directly interact with, but they're all sort of there supporting the infrastructure. Then as a researcher or data scientist, they have the option of pushing their code directly into GitHub, which will then launch their code into a little job submission cluster. The job submission cluster was a little bit hard to get our heads around. This is just a small cluster that launches your Python script, but it's not actually doing the machine learning. The machine learning is done inside of this compute cluster, which your Python code or whatever can speak the API reaches out to. This is where we have a couple options. The researcher can specify the cluster size dynamically if they want to inside of their Python code, or if they don't have funding to create their own cluster. We also provisioned, and I'm missing one here, sort of a light, a small, a medium, and a large cluster, which in theory, that could be something that the university provided at no cost, with the downside of it's going to be shared, so you might get queued before you can actually use it. In addition to the Python script input, we also have the ability to run interactive Jupyter Labs notebooks. So if a researcher is still working on that Python code, like if they want to go in and just start, changing things line by line and seeing what happens without wanting to do a full push to their GitHub repo, they can also do that using the Azure Machine Learning Studio. And then this very last part is we have the results and the data sets are both stored in a storage account that can be accessed independently of the pipelines if needed. And I'll let Steve and Barry talk a bit about our Terraform setup.
Hey everybody. So Barry and I focused primarily on getting all of these components sort of terraformed out and stampable. Terraform is actually incredibly cool. Some of the highlights that I'll toss out there. I really liked modules. I was able to modularize all of these components. So you have the Azure Machine Learning Workspace. I made that a module. I made the compute cluster a module, and we made the compute instance a module so that you can kind of come back and reuse these patterns and apply them as you see fit. In the case of our GitHub repo, we actually have just kind of I'll call back to, I think it was Michael talking about the pet names. I really despise having to type in variables on the command line. I just want to be able to hit Terraform apply and have it just generate stuff for me. So that is probably a to-do, is to sort of generalize this for wider usage. But the cool thing is within about 5-10 minutes, you have a new instance of this, and you can kind of pick and choose whether you want pre-built or on the fly compute clusters. Or if you just want to play with it, you can spin up just a single instance VM that, is very low cost. One of the things that I don't think was mentioned earlier about the compute clusters, by the way, is, and I haven't seen this very often, but it actually allows you to scale down to 0. And when it's not running, that means you're not paying for it at all. And then you can also set a timeout, I think, of up to 72 hours to have sort of ready state baselines to be able to run a pipeline. And if you need to scale out, it'll scale out to your maximum. So it's a pretty good cost control measure, in my opinion, that allows you to just have something standing out there and scale up and down as needed. But back to the Terraform, an additional component that we added was Terraform state saving within an Azure storage account, so that we could all kind of work together on the same project and not have to worry about state drift or stepping on each other or unintentionally pushing at the exact same time. So that's pretty cool, and I may actually try to integrate that in there as well as an additional module. For those that aren't aware, that's basically using an Azure storage account or an S3 bucket or something like that Terraform will use as the backend for storing the state. And then it supports like lease acquisition and release at the same time, so that, like I said, Barry won't step on me while I'm making a change, or vice versa. I think that's about all I have. You can actually see the resources that were provisioned on the slide, so I won't go into that too much. We were going to do a demo, but unfortunately today, just like all live demos go, for some reason the Azure Key Vault provisioning service is very slow. So provisioning is taking somewhere on the order of 20 minutes, and 18 of that is Azure Key Vault provisioning. So we're just going to skip the live demo. Barry, do you have anything to add?
No, I just add Steve set up a lot of the skeleton of this Terraform initially, and whole thing was brand new to me, the Terraform concept idea, and I'd never touched it. So I I took the task of just pushing in the compute cluster as a proof of concept into the Terraform build. And it was a lot of fun. Some of the challenges I ran into is like we have multiple subscription IDs set in our Azure instance. And, I was using some default subscription ID and trying to push things up, and it was giving me errors on the plan portion of the Terraform planning. And so that was one, and various other things similar to that you had to have knowledge on the Azure side of what you're working with and where you're building into and stuff like that. And various another couple small challenges were the special characters it doesn't like, and some of the names in Azure for like resource group and whatnot, or maybe more the assets within the resource group. One other thing, it just slipped my mind. But yeah, no, I had a lot of fun with it. Oh, the other thing was destroying things, the destroy feature. There's the apply feature, you're applying your Terraform, but this destroy was fascinating to me, where you can just completely destroy everything you've created and run it all over again. So anyway, I just thought I'd throw that in as some of the things that I observed and had fun with.
Maybe the key vault is going so slow today that just not enough people working on a Friday to give Microsoft enough entropy to keep that stuff going. So this is what the Jupyter Labs notebooks look like inside of Azure Machine Learning Studio. Lots of words there. It is not quite as good as a normal Jupyter Hub interface, but I think it's functional and it seemed to work enough for us to test. Outcomes, and we sort of talked about this already, but we have this working pipeline that can be used as a template by researchers or data scientists. I think we all learn like a lot. We probably all learned slightly different things. Like I think a lot of it, some of us had Terraform experience, some of us had Python experience, but nobody had like all of the experience really needed to pull something like this off. So I feel like we all learned something new in there. And again, not to harp on it too much, but I really like how, and this was just sort of a happy accident that we found, was being able to have either these pre-built clusters or giving the researcher the ability to create their own cluster. And then having these compute clusters scale down, like Steve mentioned, scaling down to 0 is great because then the researchers aren't paying anything for these resources that they aren't using it, or our central IT isn't paying for them while they're not being used. And we talked about this already, but why did we want multiple clusters? And mostly like different funding models. Some people are going to have a lot of money to use. Some people aren't going to have any money to use, and we want to be able to support them both. This is just a little screenshot of to give you an idea of the metrics that we're getting out of Azure Machine Learning Workspace. The red bar represents idle nodes and the blue bar represents active nodes. So as we were running our tests, we can see all these idle nodes spinning up, they get used, and then eventually spin back down. This was helpful in like troubleshooting because a lot of times we thought we might be using all of the nodes, but in reality, we were only using like a set number of them. And that was because there were some hard-coded numbers in the Python script we were using that needed to be variabilized. Challenges, there were a lot of challenges, but the ones that I think came to mind for us were testing was sort of time intensive. We would launch these jobs off and sometimes we would have to wait they wouldn't fail immediately. We would have to wait 30 minutes or an hour for it to get to the failure. We probably could have worked around that if we knew more about like how these scripts actually work, but we were still learning all of this. So testing took a lot of time. We're saying we're comprehending the Azure ML workspace and studio concepts. I would probably expand that a little bit to like all of the Azure concepts. Just sort of getting on board with that was not the easiest thing. Azure permissions were not super easy to figure out either. I think we have a better handle on them now, but that was a stumbling block trying to get around those. And then one other sort of stumbling block is we also wanted to try, in addition to having these Azure ML workspace clusters, we wanted to have Kubernetes clusters. And we never got that fully going. We tried both some internal Azure clusters as well as using Azure Arc to connect to some clusters in GCP, and we never really got either of those totally working. Long-term goals, and we're almost at the end of this presentation here, and then we'll get into the little demo. Deploying right now, we're just deploying Terraform like from our laptops. And since Steve was getting the state into an Azure storage account, I think sort of the next step would be getting these running out of GitHub directly, so we wouldn't have to even change it on our laptops. We would just make the changes locally on our laptops, and then the Git push would deploy and make the changes. We'd really like to get Jupyter Hub as an alternative to Azure Machine Learning Workspaces in here. We had looked at doing that originally, but the Azure version of that, which was the Machine Learning Studio, had a lot of really good integrations that let us like just get up and running super fast. So we just went that direction. But given more time, we would like to actually implement real Jupyter Hub notebook style interactions on there, which seems to be what most researchers like. Mentioned it before, but the Kubernetes integrations, we'd really like to see that as well. It could give us some cheaper compute than what we're getting from the from these little Azure clusters. Yeah, so I think that would be great if we could get that going at some point. And then I think I added this last one, is just Terraform is no longer fully open source. So there's a fork called Open Tofu. So our Duke and Duke leadership is very interested in utilizing things that are like real open source. So we would probably switch to the real open source Terraform, not the source available Terraform for long-term support. And now we'll do our little demo from Jim, acting as a researcher, actually doing some work on here with all this stuff.
Sure, thanks, Drew. I'm going to share my screen. Let's start off at our README. You know, one thing we spent some time doing is running these notebooks and choosing one to understand how the workspace functioned, and we're getting results. We're pretty happy about that, but we wanted to create some way of interacting with this workspace that was not part of the Azure stack. As tasty as that Kool-Aid was, there is a CI/CD pipeline function inside. However, we wanted to try to make these things work from the outside and understand how to trigger the correct actions and provide the correct authentication. And this turned into more of an exploration of the Azure roles and the details of how service principles work. As far as creating a Git-based workflow that deploys code somewhere, that's something we do all the time. Typically it's GitLab and it's to a Kubernetes cluster. It's not GitHub into an Azure machine learning workspace. There was quite a bit of differences and challenges. So started by taking that notebook and turning it into a script that wrapped the primary work into a function and took arguments. And there was a YAML syntax and some Azure command lines that can send that into the cluster, and it worked. And then found some examples online, which I forked one to modify to our purposes. It contains over 300 examples of how to do this for various types of jobs. Would certainly recommend following that original repository if you're interested in looking at how they structure the workflows. And they have wrapper scripts. Took some time to understand, learned a lot about options that you could pass into this command line to get a certain type of output that is useful when you're trying to monitor the progress of a job. And so in doing that, just one caveat, if you do that, there's over 300 jobs and you don't want to configure it globally to be able to talk to your workspace, because a lot of them run on crons and they'll just fire up and start running. That happened, but I hadn't done the configuration. So I got a lot of emails and burned some GitHub action minutes, which were free, so that was fine. But I reforked it and nuked everything except these little examples as far as the workflows go. So that was just a little gotcha, and again, it contributed to the sort of express learning situation. So the simple one was we've done a lot of Azure specific things, and so what we wanted to do is take an existing MIC taxi data AutoML type job and just run it. It has no Azure specific code in it. It just needs to be pointed at a compute. And we figured if we successfully could not only point it to the manually created workspace, but if we could just stand up a one with Terraform and don't touch it at all, and then change a few parameters in GitHub, and it runs there, and that did work exactly as intended. So here I've included links out to the job definition and the GitHub workflow. So this was taken from the other. This was their main example. I wired in our information here by providing secrets and specifically only providing the env right there. But otherwise, I didn't have to do much here. I left their Bootstrap resources in here. I wanted to understand the script. There's a variable you can set. It would like stand up something for you to deploy this to, but it's turned off by default. And so in our long-term example, probably would strip out most of this. But there's a run job shell script that they provide that adds some of those niceties I didn't have when I was using the command line directly myself. And let's see. Here's an example of a pipeline that ran successfully. Each of these stages had some useful logging about what was happening in the cluster as it did. Earlier when we were trying to figure out how to log in, these errors were quite useful. I didn't understand that a service principal was represented both as a user and application. Steve helped me realize that I needed to find the application object and authorize that and generate those credentials. So those are some of the gotchas that really consumed a lot of time in learning how to navigate those details for what is otherwise a fairly familiar process. And then over here, here's an example. No, that's the bank job, not the pipe. Okay. And so here's a pipeline we've deployed and already run. Again, these take a while. So in this demo, we just got a few minutes. I'm going to kick one off and you'll see it start, but then that's kind of it. And then we also have the Python that needed to authenticate to deploy its own compute. So we have the small, medium, and large runners you can target directly. I set the taxi job to target the medium cluster. I set the Python job to target the small cluster. And so it just ran its script and used the authentication we passed in to spawn a larger cluster to actually do its own work. I don't know if that's as much of a production use case as a development use case, or if you had complicated logic that needed runtime criteria to target different computes, even if you did not grant the rights to, because we had to find the rights to authorize this to happen. But those are not the same as targeting an existing compute. So even in a more limited account, you might need to determine where you need to run on the fly. And so that example kind of demonstrates that. And so here, I kept these manual for now, but all the various things you can do in GitHub can be done, webhooks or a pull event or all those manner of events that are not Azure specific can trigger these jobs. And this starts the build. And this takes a few minutes. It's going to appear here in the jobs when it gets down to that, if we have time. If not, hopefully the logs of the runs here will prove that we did in fact do that. So as far as takeaways from this, turning this into a truly reusable template, I think is going to be a couple of steps. And one is sort of learning from those router scripts and pulling out the things we don't need. And also, as far as the Python SDK for dealing with Azure, there is I believe a simpler way to write one type of credential retrieval that use a hierarchy of methods, so we don't have to pass. The script doesn't have to re-authenticate while it's running. That created some challenges. However, we sort of worked around that here in the workflow. The job itself declaration is static, but we have dynamic things here. So I used our secrets to template out the job so it could run with the right environment set when it was shipped out to the cluster. I think we're right at 2, so that's all we have. I don't think we're going to get this to show up before it. Right, it's going to be another minute before it actually says that it's submitted a job and it's been accepted. There we go. Gentle Brick is now going to be in Subtle Raptor here shortly. There it is. Okay, and we're running. And it's starting to work through its pipeline. So, and that was it.
Live demos.
Yeah.
Great. Are we finished? Did you guys have another slide, or can we move on to questions? No, that was it, the end. Okay, great. Fantastic. That was a great demo, just right on time. We'll take just 1 more minute to wrap up because we are at time. So there is one question, which is, how do researchers get to choose the size of the virtual machines, or are these all planned to be abstracted from them? I know this is just kind of a work in progress, but if you think about it, what would that look like?
Honestly,
So I
either.
think-
Right, Drew? Go ahead.
Yeah.
You,
Yeah, they would specify it in their code right now. So if they wanted to use one of the pre-existing clusters, we would need to provide them with the names of the clusters, and they could specify that in their code. And then if they wanted to make their own, we would just need to provide them like a piece of sample code on how to create it and give them access to create it. So it's a pretty small block of Python. It's maybe 5 lines, but that's something where if they had the funding for it, we would say, okay, yes, they can spend this money. And also, like, here's a sample, fill in your VM size and the max nodes for the cluster, and then they could spin it up with that.
Great. That's great. And this whole presentation actually sounded a lot like an advertisement for Terraform. And then every time somebody mentions open tofu, I keep thinking it's IAC for vegans. So I need to wrap my head around that. But thank you, everybody, for joining today's final presentation for the Class Advance Cohort 6. That's a Spring 2024 cohort. Just amazing presentations. I will be sending out the Zoom recordings to everybody on this call, along with the slides if you're interested. And with that, thank you once again, and thank you to all the presenters. We'll see you all later. Bye.